Good morning, Astronomy 1020. Welcome back to our second week of lecture. Today begins lecture 2. We're going to learn about the nighttime sky and stellar coordinates. I've got a fun lab in store for us today. We'll be doing lab number 2. Lab number 2 involves playing around with this celestial globe so that we can get some hands-on practice using stellar coordinates. This is actually a really cool lab when we get to do it in a lab room together, because then you kind of get your own globe and you can poke around and learn the names of some famous stars. I wish it could be like that, but you know, COVID-19 and all. So we'll do it together using my borrowed iPhone 7 as a remote camera, and we'll see if we can get the gist of it together. Please make sure. I need to put this somewhere. Please make sure that you have lab 2 printed out before we get to lab. And as I was just talking with Nick about, I also provided a document, a Microsoft Word version of today's lab. Personally, I like the PDF, so I'm printing out the PDF and I'm going to write on that. We just need the first 2 pages. But if you don't have a printer, you could use the Word document version, and you should be able to use Microsoft Word. Okay, I don't feel like downloading that, but you should be able to use the Microsoft Word version, the program Microsoft Word, and fill it out using your computer and submit it that way. So that will be helpful if you do not have a printer. I also need to make a couple of lame announcements before I get into the astronomy stuff, only because I've been getting so many emails with the exact same questions, and I'd like to try to address that question. The first one is, people keep writing me and saying, I'm confused. I thought this was an asynchronous class. Why are you making me come to a live session? I have work. And the answer that I thought I made clear in the earlier videos was, you don't have to come to this. I have the lectures already recorded. And I don't think this applies to you guys that I'm looking at, because you're obviously here, but for anyone who's watching the video later, you can just watch the videos at your own time. However, if you would like the option to hang out with me live while doing this, I, out of the goodness of my heart, am taking this time to redo the lectures live so that people can interact with me. I find that fun, maybe some of you do as well. But there's no obligation to be here live, since not only am I recording these sessions, but I have the previous semester's recordings as well, and they're roughly identical. All right, so that's one question. The second question is, hello, I have anxiety. Can I turn in my homework late? And here's the deal with late homework. You don't have to do it the day I hold the lectures, but you do, no matter what your circumstance, absolutely have to turn it in by Saturday or maybe Sunday morning at the latest. And that's because the administration has doubled my class sizes so that I now have, think about this, guys, 168 students this semester. There's a lot of you. And considering that I have a lab and a homework to grade from each of you each week, that means by Sunday, I have up to 336 papers to grade. Now, let's say I could grade 1 paper per minute, right? Let's use dimensional analysis here. If you take, let me go to speaker view. I just want to make this really painfully clear because apparently I haven't yet. 336 minutes. Let's say I could grade 1 paper a minute, which would be crazy because it sometimes takes 30 seconds just to like load the little page and look at it. But if I could grade 1 paper a minute divided by 60 minutes, that's 5.6 hours of work. Now, if people start turning stuff late, that could balloon to up to 10 or 11 hours of work. And I just don't have that much time on Sunday. So I have a hard rule. You know, you've got up until Saturday or Sunday morning to get your lab and your homework in, no matter what your circumstance. But unfortunately, once I grade it on Sunday, that's it. It's cut off. I deactivate it and it's a 0. And I think that's plenty of time to watch the video, considering that I do the work with you. I think that should be factored into it. So I don't think that's an issue necessarily for anyone I'm talking to live, but it could be an issue for people who eventually watch these videos later. You need to understand that that's a hard and fast rule. I don't know if anyone has any questions about that, but hopefully that's clear now. Okay, so I did want to go over dimensional analysis again, and I wanted to teach you guys about how to make a scale model of the solar system. That's kind of a fun exercise, but I think knowing me, I'll end up dragging that out for 20 minutes. And considering that we need to get to celestial coordinates to do our lab, I am going to get into the celestial coordinates in the nighttime sky first, and I'll only do the scale model of the solar system if there's time at the end. So you guys are going to get a flurry of vocabulary words. And I think probably what we're going to do is we're going to return temporarily to the discussion of Earth's orbit. You guys will remember that in our last lecture, I started off teaching you guys a little bit about the orbit of Earth around the sun. And we're going to kind of build off that so that we can transition into thinking about the nighttime sky, function F520. So we're about here in our slideshow. So far, we've talked a little bit about the fact that Earth's orbit has a perihelion point and an aphelion point. Let's see if you guys remember any of this stuff. Let's go over to the board here, and let's return to Earth's orbit. You guys remember that we talked about Earth's axis spin. I'm not going to redefine everything because I've already done that. We talked about Earth's orbital period. We talked about the fact that in space, counterclockwise equals what direction in space? Students, tell me what you know.
East.
East, very good. That's going to feature very prominently in today's lecture and in today's lab. So I'd like to remind everyone that in space, counterclockwise is east. I'm doing this a little bit quickly because I already covered this. I'm just kind of reminding you what we had done there. Then we learned some vocabulary terms. We learned about the term perihelion. Why don't you guys remind me what perihelion means?
That is the point in the orbit closest to the sun.
Thanks, Mia. So that's closest to the sun. And then we learned about the aphelion. That's the farthest from the sun. I'm kind of redefining them loosey-goosey. And then I talked to you guys about defining a new unit in space, the astronomical unit, which is equal to 150 million kilometers. So far, so good. That much I think you've got in your notes. And then we kind of went on a digression on dimensional analysis. And that took a little while, but it was not a waste of time, I promise you. Let's pick up here and let's continue talking about the orbit of Earth. I've got a new vocabulary term to define for you. It's called the ecliptic. And if you guys look at this lovely picture from your book here, the ecliptic has several definitions, but the first and the easiest one is just it's the quasi-circular path that Earth takes around the sun. So if you could imagine Earth traveling on a little track, the name of that circular track is called the ecliptic. Let's get that on the board. And sometimes people refer to that track as the ecliptic path. And the ecliptic, this is definition number 1, is just the path of Earth around the sun. And in addition to describing the ecliptic as a path, if you think about it, when you draw a circle in space, that circle defines a two-dimensional plane, like a tabletop, right? Because a circle is inherently a two-dimensional object. And we refer to that thin glass here as the ecliptic plane. And that's an important reference point. Come on, somebody's calling me. Let me make sure this isn't critical. Nope. Okay. The ecliptic plane.
Where the fuck is that from? Stop. Stop. Stop.
Sorry,
Stop.
someone have a question, or does someone just forget to mute their microphone? Let's find you. Gonna find you. Who are you? Nope, can't find you. Okay. If you have a question, feel free to shout it out, but otherwise, hide non-video participants. Okay. Oh, Jessica? Yeah.
When you're writing, can you switch the view just because I can't really see the board?
Oh, did
when
I
you're
not
actually
switch
writing?
the view?
No.
Wait, so do you see it when I switch the view? Do I control your view?
When you put it so that you're presenting, I think we see the slides, but you changed it before where that board was closer so that we can actually see what you're writing. I can't see it in the format that's right now.
Oh, okay, wait, I want to understand you, Jessica, but I'm not sure I do. You're saying that I'm doing the board differently than I did it last time?
The view on the screen is different. I don't know if anybody
Okay,
else
I think I see
can
what's going on.
speak on that behalf.
Jessica, I don't control your view. You control your view. So Jessica, I want you to move your mouse to the upper right-hand corner. It'll say view with some little dots. Now click that view and go to speaker view,
Okay,
and then
got it.
double click my face to lock speaker view. If you don't double click my face, anyone who talks, it'll jump back and forth. So make sure you double click my face. This is lock speaker view. You control that, not me. Does that fix things, Jessica? Okay. The ecliptic plane is a two-dimensional surface made by the ecliptic. And if you think about it, the ecliptic plane is sort of like the disk of the solar system. And the reason why it's the disk of the solar system is because within a, hold on, guys, I need to turn the heat down in my place because I'm starting to sweat. Hold on a second. All right. The reason why the ecliptic plane is the disk of the solar system is if you look at the orbits of the planets, I'm going to go to Google for just a second here, and I'm going to type in inclinations of the planets. I don't know if that'll work, but the orbital inclinations of the planets. Look at this crappy slide for a second. Wow, that's really low res. Well, whatever. Hey. Just a second here. Usually this comes up. Orbital inclinations of the planets. There we go. That's a slightly bigger version. Okay. No. This is what I want. Sorry. If you look at the orbital inclinations of the planets, if we define the Earth-Sun line as the ecliptic plane, which you guys can see here, all right, to within a small number of degrees, the other planets tend to orbit the sun also on the ecliptic plane. Mercury's a bit whack. 7 degrees is actually a pretty high inclination. Venus goes above and below by 3 degrees. Mars is 2 degrees. Jupiter's 1 degree. Notice that all the planets are somewhere between 1 and 3 degrees. Pluto is a whack job. At 17 degrees, its orbit is actually inclined a lot more than the other planets. And that's just yet another reason why Pluto's been demoted to an overgrown comet rather than a planet. You know, it didn't have to be that way. There's nothing at all in the laws of physics that would have prevented, if this is the ecliptic plane here along the yellow stripe, there's nothing that would have prevented some of the planets from just orbiting cockeyed at any old orbital inclination they wanted to. You could have had a solar system that looks like one of those drawings of the Bohr model of the atom with planets rotating in all different directions. The fact that they don't, the fact that all 8 are rotating in roughly the same plane means something. It means something about how the solar system formed, that it was a cohesive process where some cloud collapsed and started flattening into a disk. So there's a reason why all the planets orbit within the ecliptic plane, more or less. It's not perfect, but to a first degree, you can say that the ecliptic plane is the plane of the solar system. Now, in today's class, we're going to concern ourselves with observational astronomy. That means what happens when you step out your door into your backyard and you look up at the sky? Can you make any sense of what's going on there? And if you take an Earth-based perspective, the ecliptic becomes something a little bit different, okay? So this is an Earth-based reference frame where North Pole is pointing up. Notice that the projection of Earth's equator, the celestial equator, is this red ring. And now the ecliptic is no longer the path that the Earth makes around the sun. The ecliptic is now the path that the sun makes against the background stars over the course of 1 year. And you can see from slide, I think it's 55. Let's try, oops, not 55. From this slide, you can kind of see it's the same thing, right? The green circle is the path of Earth around the sun. But if you're on Earth, the sun is also pegged to the green circle as it rotates against the constellations of the sky. So let's write down that second definition of the ecliptic. This is ecliptic definition number 2. Path of the sun against the background stars. Class, does this remind you of something that we talked about in our last week's lecture? What does this remind you of? I thought we had a discussion about the path of the sun against the background stars.
Hold on. What was it again?
I'm asking you guys if this definition reminds you of something from last week's lecture.
Is it the small angle formula?
No, not at all.
No.
I'm thinking of something else that was part of our original discussion.
Does it have something to do with the zodiac? Because that's where the sun travels.
Yes, Mateus, that's exactly what I wanted you to say. Remember, when we were talking about that astrology snake oil stuff, we were talking about the fact that the sun travels the path of the zodiac. So in a way, Mateus, what you've realized is that the ecliptic is the zodiac, and the zodiac is the ecliptic. For instance, Mateus, as an astronomer, when I go out at night and I look at the nighttime sky, you know, Vishnu wasn't kind enough to paint the ecliptic on the heavens for me. I don't have a marker or a line that travels the sky to show me where the ecliptic is. I actually have to look for constellations that I know. And when I'm hunting for a planet, I look to the sky and I look at Taurus. I look at Cancer and Gemini and Leo. Cancer is actually kind of hard to see. I look at Sagittarius. When I see those constellations, I know that's the disk of the solar system, And that's where I'm likely to find other planets. I would never expect to see Mars in Cassiopeia, or I would never expect to see Mars travel through Orion, because those are not zodiac constellations. So that's how I can tell where the ecliptic is when I'm looking up at the sky. That's a good rule of thumb. Both definitions of the ecliptic are important in this class. Okay, how do you guys feel about me erasing? Does everyone have all this down? Cheyenne, looks like you're writing. How are you doing? You're good. Thumbs up.
Really blurry.
Andrew, are you okay? Okay. I'm going to erase now. Let's also consider that Earth, as it travels the path of the ecliptic, is kind of tilted. And you might have noticed this by looking at the pictures, or you might have noticed this by looking at a globe. I don't know what slide I'm looking for here. Let's try 22. Wow, that was exactly the right number. Earth has a 23.5 degree axis tilt with respect to the plane of the ecliptic. Actually, if you're going to get technical, it's tilted 23.5 degrees with respect to the perpendicular to the ecliptic, but that's kind of like TLDR. So we just say 23.5 degrees with respect to the ecliptic and call it there. And I want you to notice that as Earth travels the sun, as it travels the path of the ecliptic, that 23.5 degree tilt kind of maintains the same orientation in space. So for instance, if it's tilted up in that direction, as it travels the sun, it's keeping that tilt. This is more impressive when you're in the same class as me, but it kind of stays tilted over there, and it maintains that direction as it travels through space. So Earth's most of the other planets have axis tilts, and some of them are pretty wonky. Earth's is 23.5 degrees with respect to the ecliptic plane, okay? Because it maintains the direction of the tilt, right? Because the tilt kind of points up in the same direction towards the North Star Polaris, as Earth travels the sun, it makes 4 key alignments along the ecliptic. And these are geometrical alignments where the axis tilt, either the North Pole is tilted directly towards the sun or directly away from the sun, or it's kind of at a 90-degree angle to the sun, and the northern and southern hemispheres get equal amounts of sunlight. And I just refer to those as the 4 key points in Earth's orbit. Let's write them down. Four key points in orbit, and these are geometrical alignments, are the spring equinox, which occurs around March 21st. The summer solstice occurs around June 21st. The fall equinox occurs around September 21st. The winter solstice occurs around December 21st. You guys may have heard that it's actually 365.25 days per year, or 0.24, depending on its tropical year. The date actually slips from the 20th to the 21st to the 22nd to the 23rd and back. It kind of wiggles back and forth by about 4 days because of the leap year business, right? So for instance, we've left the winter solstice and we're now heading towards the spring equinox. Why don't we see what day the spring equinox is this year? Maybe it will fall during one of our classes. Spring equinox 2021. Come on, baby. It will occur on Saturday, March 20th. So we will not see each other on the spring equinox. That'll be just after spring break, okay? I want you guys to start off, you can think of these as dates because there's a date pegged to every point along the ecliptic, but I want to stress that they're also geometrical alignments. Let's take the summer solstice. Could you guys all imagine that you, the viewer, at the camera there, you guys are the sun, okay, where my finger is pointing. And the day of the summer solstice is the day when, watch this, as Earth is rotating, there will be one exact day, in fact, an exact moment in time, when the North Pole is pointed directly towards the sun. And that day is the summer solstice. A day before, the alignment isn't perfect. A day after, the alignment isn't perfect. The exact date and moment of the summer solstice is when the tilt points towards the sun. Likewise for the spring equinox. The spring equinox is that exact moment when the Earth's equator is pointing perfectly towards you, the viewer. A day before or a day after, it's not as perfect an alignment, but this is what the equinox looks like. You get sunlight on the northern hemisphere and the sunlight on the southern hemisphere equally. So the equinoxes are when the axis tilt makes a 90-degree angle with respect to the sun, if that makes any sense. Let's see if you guys get it. I'll test you. How about that? Get ready for your test. What day is this? What day is it?
That is March 21st?
No.
No, oh, my bad.
June 21st.
Somewhere?
September 21st.
December
Wow.
21st.
Yeah,
Oh,
who said December? December wins. Who said December?
Kelly.
Hi. Oh, Kelly, you're a troll. I forgot. Kelly the troll knows what day it is. Kelly, how did you know that was December? How did you know that was the winter solstice?
It's it's turning away from the sun.
Wait,
the,
what's it?
the
I
axis
love-
Oh, the
tilts
North
away from the sun.
Wait, what is it? What's turning away from the sun?
The axis tilt.
Well,
The
the
North
axis tilt is actually turning towards and away from the sun. Maybe you should pick a point on the axis. You don't understand what I mean, but let me explain what I mean better.
It's the North Pole, isn't it, that you're referring to?
That's right, Sabrina. I would have said the North Pole is pointed away from the sun. Remember, the South Pole is also on the axis, and the South Pole is pointing towards the sun, right? You have to remember, guys, that the sun is coming from over here. The sun is over here somewhere, right? And let me make my point clear. Kelly, this is the axis, right? So some of the axis is tilted away. The north axis is tilted away from the sun, but the southern axis is tilted towards the sun. That's why when you said it, or when you said the axis, I was unsatisfied because it was not clear. Being able to use our vocabulary terms to be clear is actually a challenge. That's one of the challenges we're working at here. Okay. Anyways, my point is these are geometrical alignments. Now that you understand a little bit about Earth's orbit, what we're going to do is we're going to try to change our reference frame so that we can think about, we want to think about what it looks like from an Earth-based perspective. And I want to remind you guys that we learned a little bit about angles last time. And angles are going to be important to describing the positions of objects in our sky. I'd like to remind you that we have degrees, but when we want to get into smaller angles, we can also use arc minutes and arc seconds. And I gave you the conversion factors for those last time. Expect me to be using them. Okay, so let's take a look here at a model of something called the celestial sphere. This is what we're going to be using in our labs today. The Greek astronomers literally believed that all of the stars were fixed to a crystalline sphere which rotated around the Earth. That is obviously not true. Today we know Earth travels along the ecliptic and orbits the sun. We also know that stars lie at a variety of different distances. But in a way, you're not really ready to think about that just yet. You guys need to start thinking about the sky as a rotating sphere so that we can track the angular motions of stars across our sky. So basically, we're going to define the celestial sphere in the same way the Greeks did, because it's useful to think of the sky as rotating around a fixed Earth. That's what it feels like when you're outside in the desert watching the sky rotate overhead. And I mentioned the desert because the desert is one of the best places to look at stars because there's usually no obstructions along your horizon. So let's start with a few ideas. Let's talk about the celestial sphere. The celestial sphere is a useful lie. It is a sphere of infinite radius. That basically means we're not going to worry about the distance. We're just going to imagine it as infinitely far away. It's a sphere of infinite radius on which stars, the sun, the moon, planets, galaxies, hell, anything you can imagine, anything that's up seems to rotate. And we can identify places on the celestial sphere to use as reference markers. Those three locations are the north celestial pole, which is basically the projection of the North Pole onto the sky, the south celestial pole, the projection of the South Pole onto the sky, and then the projection of Earth's equator onto the sky is the celestial equator. Let's define those. So we have the north celestial pole is projection of the North Pole onto the sky. Celestial equator is projection of the Earth's equator onto the sky. And I think you guys get the idea. Then we also have a south celestial pole, which I'll just save some marker space and not define that because it's obviously the projection of the South Pole onto the sky. Now, students, if you're standing in your backyard and you're looking up at the sky, are you going to be able to see all the stars on the celestial sphere? Cheyenne says no. I was hoping this would be obvious, but sometimes things that I think are obvious aren't obvious to you guys. So explain that to me, Cheyenne. Why can't I see all the stars at night?
Sorry. One of the reasons you can't is a couple different factors. It depends on sorry, I'm like blanking right now.
That's okay. It can be actually difficult to explain these. You can know the answer, but not know how to explain the answer. That's something that we're going to practice with Cheyenne. So I feel your pain. That's kind of why I'm making you do it. So let's say I'm standing here in the Rock of Gibraltar. Which stars am I going to be able to see, Cheyenne?
I'm sorry, what was the question? Sorry.
Are you having a, all right, I'm saying if you're standing where this arrow is, Where are the stars? What stars will you be able to see?
The stars within the northern celestial pole.
Sort of, yeah. You'll definitely be able to see some stars up here, right?
Yeah.
You definitely won't be able to see some stars down there because Earth is in the way, right?
Yes.
Okay. Now I need to enhance that picture. See, when we step out onto a position on Earth, we have something called our local sky sitting above our heads. It's like a hemisphere. Let me show you a little picture of it. So when you step outside into a field, the sky that you see is what we call the local sky. It's the sky that's available to you. Let's forget about the fact that sometimes there are trees and buildings in the way. That's very frustrating. But if you're at sea or if you're in a desert, you're on a flat plain, you can kind of see a full dome of the sky. And I have an important lesson to teach you. You can always see 1/2 of the celestial sphere from your local sky. And that's not an obvious point because if you're standing over here where this arrow is, you tend to think of yourself as a little dude on a big Earth. And you try to imagine that the sky above you is a little sky surrounding your little dude head. But in fact, your sky is a big dude sky. I shouldn't use confusing colors here. You can actually see all of this. And that's because the Earth is infinitely small in comparison to the celestial sphere. So Earth doesn't really get in the way. Let's write that down because that's not always obvious to folks, okay? I'm going to even put it in a different color because it's important. You always see 1/2 of the celestial sphere in your local sky. I want you to underline local sky because that's a key vocabulary concept. Let's put an exclamation on that side too. You always see 1/2 of the celestial sphere in your local sky. Okay. I'm going to erase. Kiana, are you still writing?
Yes, I need a second.
Could you wait
Sure.
a little
I'll
bit,
sip
please?
some iced tea. That gives me some iced tea time here. Where'd you go? Are you set now?
I'm good.
Okay, I'm going to erase. Okay, we've been building up towards this. Now it's time to talk about the local sky, and then we're going to do some coordinates. The stuff today is a little bit technical, not exactly fun, but believe it or not, actually useful if you want to learn how to become an amateur and enthusiast and be able to find objects yourself. So let's talk about what are called the fundamental positions of the local sky. So basically what I'm going to do here is we're going to have a little Bob Ross moment where we learn how to draw a 3D view of the local sky, all right? Leave yourself quite a bit of headroom here. You're going to need a ruler or a straight edge for this. If you do not have a ruler, the edge of your calculator will do. Make a line that's, I don't know, let me see here. If you have a piece of paper, maybe 10 centimeters or so would be a good line. 60. Leave some headroom. And draw a line in the middle of the page. If you made it 10 centimeters, you can mark the midpoint by putting a dot at the 5 centimeter line. And then you can make another one. You can make a 5 centimeter dot right above the midpoint. And that will allow you to kind of, actually, I like to make a couple of them. I like to use the radius, 5 centimeters, to kind of mark a couple of, connect the dots so I can draw a nice dome. So I'm drawing 5 centimeters from each of these positions here. Okay. And now what you can do is you can kind of draw the best dome that you can do freehand by just kind of connecting the dots, okay? Okay, next up, if we want to make it three-dimensional, put a little dash above and below the center dot, and then you can kind of draw an oval by connecting those dashes to the edge. And this can be your ground, like the field that you're standing in. If you're feeling artistic this morning, this afternoon, I suppose, you could even shade in some grass. Draw some happy little grass. Okay. And that's not too bad. I've seen worse. It's very important if you're going to draw your local sky that you choose the cardinal directions. I am a right-handed person, so I always choose north to be right. I just kind of do that instinctively by convention. And then I make south on the left. That means east is towards the observer, towards the plane of the board here. And west is into the plane of the board. Sorry, east is out of the plane of the board. West is into the plane of the board. It's very important you choose north, south, east, west. Now, I want to warn you that the book also makes some diagrams like this, but the book is constantly putting north on the left-hand side. And I suspect it's because the artists that they hired to draw those pictures were sinister left-handed people who didn't know any better, okay? But we won't make their mistake. We'll make sure, or if we do look at their diagrams, make sure you remember that theirs are going to be reversed from mine. I kind of have a mixture of both in my slideshows, unfortunately, because I am not a talented graphic designer. Luckily, this one, which is the most important slide here, has north in the same orientation, okay? All right, let's define, you are an observer. You're standing here at the center of the field. Put a little dude there, okay? And now let's draw a line through the dude's head right up to the very top of the sky. And this line points to a particular location on the sky. This line points to your zenith. So you can mark it with a Z, and we'll define that vocabulary term down here. The zenith is the point overhead. We can also take a moment to define your horizon. The horizon is a 360-degree ring at the base of the local sky. So that means this, that ring that oval that we drew there, that's your horizon ring. I also want to define another key vocabulary term. I want to define the arc that runs from the northern horizon up through the zenith and down through the south. That arc, which slices your sky in half, is called the meridian. Is an arc that rises due north, reaches your zenith, and then sets due south. So it goes north to zenith to south. Sorry, things got a little messy here. Let me try to write that again. That's fine, Marshall. Make sure you watch it later. It should be up. By the way, it takes a little while to render these videos. Last Tuesday was horrible. It took like hours and hours. I'm hoping it'll go faster, but we'll see. Okay, Marshall, it'll be up there eventually by 6 p.m. at least. Let me give you a little hint about why the meridian is such an important line. This is a little sneak peek of where we're going with all of this nonsense. I want to show you a picture from later in our slideshow when we're going to be describing the paths and the motions that stars take as they rotate through your local sky. They actually travel in a kind of complex way. This is a model of our local sky where the green disk is the ground and this green arrow points up to the zenith. Notice north is also on the right here. The colored rings that you see are star tracks or diurnal star tracks, and these show you the motions that stars make as they travel through your sky. If a star was located here, for instance, along the celestial equator, during the night it will rise in the east, it will travel up along this ring, it will cross your meridian at its highest point in the sky, and then it will sink back down and it will set in the west. And so a star located at this position along the celestial equator, stars tend to be kind of pinned to one of these places on the sphere, and then as Earth rotates, it follows one of the tracks. What's cool about the meridian is the sort of the high point that every star will make in its journey throughout the night. In a way, the sky is like a giant rotating clock. Time is based off of the rotation of the sky. Many reasons for that. But I sort of think of the meridian as like the 12 o'clock hand of a star, right? It's sort of the highest point in the motion of the star. Okay, now let's imagine that we are an observer not just in any local sky, but let's imagine that we are in the Rhode Island local sky, which means we are in the northern hemisphere of Earth. That means we're going to be able to see the North Celestial Pole in our sky. And let's draw the North Celestial Pole in by making a line from the foot of our observer and have it slice through the sky somewhere. This is our North Celestial Pole. I label it NCP. In addition, we can also draw in the celestial equator. This is a little bit tougher to draw. We have to make a ring that's perpendicular to the North Celestial Pole, and the ring has to go east to west. So what I'm going to do is I'm going to kind of make a dot that is sort of perpendicular. I'm not super good at this. My art skills are crude. And I'm going to draw from west up, from east up, and kind of make a ring. Notice mine's kind of lousy there, but let's label that CE. CE is an abbreviation for the celestial equator. There is a crazy person shouting on the street outside. I don't know if you guys can hear that. Downtown life, you can't miss it. This is a really great diagram to be able to draw because it can help you figure out how to orient yourself in the sky. Students, there's a special object located at the North Celestial Pole. Do you know what it is? What's the special object?
The North Star.
Yes, and what's the name of the North Star?
I'm not sure.
It's called Polaris. Let's draw that in. The North Celestial Pole is approximately where the star Polaris is located. And Polaris is a reference point for Northern Hemisphere observers to sort of see where the North Celestial Pole is. Let me tell you a little bit about Polaris in my slideshow here. Polaris is, it's right here, nice. It's part of a constellation that's sort of known as the Little Dipper. It's actually called Ursa Minor, the Little Bear. And Polaris is the tip of the tail of the Little Bear. Unfortunately, most of the stars in Ursa Minor are really dim and hard to see from a Rhode Island local sky because our local sky is very, very light polluted. Unless you're down in Charlestown or somewhere really dark, from Providence or Warwick or Cranston, I can't see any of those stars. I can see Polaris, I can see this star Kochab, and I can barely see that one. However, most of us can see the Big Dipper. Ursa Major is very easy to see. And the front stars in the bowl of the Big Dipper are called the pointer stars, because if you use the front two stars of the Big Dipper, they kind of roughly point towards Polaris. So if you're out at night and you can see the Big Dipper, see if you can use the pointer stars and identify Polaris. It's not a very bright star. It's kind of a medium brightness star, so it won't necessarily pop out at you right away. That's what the pointer stars are there for. Throughout the course of the night, stars will seem to orbit around Polaris. And you can actually do some cool astrophotography if you take a camera, set it up on a tripod, and point it towards Polaris. During the course of the night, stars will move on their tracks, and they'll seem to kind of orbit around Polaris in a circle. Now, some stars are so close to Polaris that they never dip below the horizon, and they just circle around the sky, and they are always visible. Those stars are called circumpolar stars. Let's make a note of them on our slideshow here. I'll use purple. I don't really have a good place to put this in here, so I'll draw a couple of circles to represent the paths of these stars. And up here, I'm going to write circumpolar stars. The easiest definition for them is never rise or set. Kind of a lame place to put this definition, but I'm afraid that I'll forget. And this is nice because we can kind of point to it on our diagram. So those are circumpolar stars. They never rise or set. Okay, so taken together, zenith, horizon, meridian, north celestial pole, celestial equator, those are called the fundamental positions of your local sky. And I'm going to use these vocabulary terms to talk about the motions of stars going forward today. So hang on to your hats. We got a bit to do. Can I erase? Okay. Okay. For the rest of this class, we're going to concern ourselves with coordinates. This is what we've been building up to. I've got a half an hour to do 3 coordinate systems. I think I can do it if I'm efficient, but it's going to be a little ugly because the only reason I have to cram it into a half an hour is because we need all coordinate systems for our lab today, especially the equatorial ones. So let me give you a top-down view of what I'm trying to do, and I will try to be efficient about it if I can. Our goal is to describe 3 coordinate systems that we need to describe the paths of stars in astronomy. The first is we're going to need to review geographical coordinates. Geographical coordinates, which are latitude and longitude, they tell you where you are on Earth. And as you've already kind of gotten a hint at, where you are on Earth will determine what stars you can see in your sky. If you're on the North Pole, you can see Polaris over your head. If you're on the South Pole, you can't see Polaris at all. 2, we're going to define a simple coordinate system called the horizon system. And that's a kind of basic kids coordinate system to describe the position of stars on the local sky. That's good when you want to like talk about stars rising and setting in your backyard. And then we're going to need to work our way up towards a more professional coordinate system that astronomers across the world use. And that's called the Equatorial System. And that's a fixed set of coordinates for the sky. It's sort of like global sky coordinates. We have to use these for our lab today, so I need to get to number 3 before class ends. Okay, now I'm going to zoom in. Now that I've given you the top-down structure, now we're going to talk about each one of these in turn. Okay, let's talk about geographical coordinates. We have latitude and we have longitude. These are things that you've probably heard about at some point in your life. Latitude is defined as the degrees measured north or south of the equator. So here's Earth. We define the equator as 0 degrees latitude. Don't forget, these are angles. They're not distances, they're angles. And as you march your way up, you go 5, 10, 20, 30, 40 degrees, all the way up to the North Pole, which is 90 degrees north. And then you can tiptoe down 90 degrees south, okay? So let's just write, for example, the North Pole has a latitude of 90 degrees north. That's just an example, okay? Longitudes are like tangerine slices. Lines of longitude, they run north to south, but they actually measure east to west. And what's weird about longitudes is you have to pick one of the longitudes to be the starting point. For historical reasons, people chose a longitude line that runs right through a particular point on Earth. You can see the inherent bias here. A bunch of dudes got together, probably dudes, and they decided that the first line of longitude, which we call the prime meridian, would run, let's see here, right through the front door of the Royal Greenwich Observatory in Greenwich, England, which is just outside of London. So there's this legendary observatory called the Royal Greenwich Observatory. And the 0th line of longitude is actually a line that runs right through the front door. So this is a place for nerds to, like me, to go and visit. If you want to go to the prime meridian, you can visit their gift shop. And if you stand on the prime meridian, that's kind of cool because you can have 1 foot in the Western hemisphere and 1 foot in the Eastern hemisphere. And you can take a selfie and post that to Instagram or something, right? So, of course, one of my former students did this. And they brought me my very own prime meridian pencil from the Royal Greenwich Observatory gift shop. So feel free to spoil me rotten with gifts. Yes, Kiana, I want to hear what you have to say.
So, did the is that actually the line between the north and the south, or did they just decide
hold on a
it?
second.
Not north and south.
It runs north and south, but it divides east and west, correct?
Yeah, that's what I meant. Yeah. I just want to know if that, if they decided that, or if that's actually the middle.
Well, there is no, Kiana, understand this. It had to be decided by people. Somebody had to decide.
Yeah.
And if you think about it, it's just kind of an issue of spinning geometry. Kiana, when the globe spins, the equator becomes a natural symmetry point because every position above and below is kind of symmetrical to the spinning equator. The problem with lines of longitude is if you forget about the land masses, every line north to south is the same. Actually, you can kind of see it better if you look at a blank globe. On a rotating sphere, every line that goes like this is kind of the same as every other. So you're sort of forced to pick one of these lines and say, that's going to be the origin of my coordinate system. And that's the same issue you have anytime you make coordinates. You kind of have to pick a point and say, that's going to be 0 meters or something, or that's going to be 0 degrees. So I was kind of joking about it, Kiana, but they didn't really have a choice. Since it was going to be arbitrary anyways, it's kind of cute to have it go through the front door of the Royal Greenwich Observatory. But yes, all people around the world recognize this as the prime meridian, and we all agree that that will be 0 degrees longitude, just so that we don't go crazy, you know? Okay. So let's write that down. We can define the longitude as degrees measured east or west of the so-called prime meridian. Now, it's a good idea to know the coordinates of your location on Earth. So for Providence, Rhode Island, we're going to need this for our homeworks on Thursday. Providence, Rhode Island has a latitude of roughly 42 degrees north and a longitude of 71 degrees west. In fact, students, if you have iPhones, and probably if you have those other phones that aren't iPhones, we can take a look and see. Let's see if we can look up. I think if you go to settings, I did this in my last class, and there's something called location services. Is it under general? Location services. You guys might.
If you have an iPhone, you can search it.
Oh. Yeah, I'd like to be able to. Okay, so if you have an iPhone, you just type into the search bar. Thank you. Thank you, Smarty. I need your help. Location. this. Oh, actually, you know what an easier way to do it is? I think we all have a compass app. Where did I put that? I had a bunch of tools. Yeah. If you go to your compass app, let me get my zoomer here. I need to get the Logitech controls. So find your compass app, search for your compass app. That's easier than location services. If you have a Google phone, it's there somewhere, but you're on your own because I don't know how those phones work. Come on, Logitech. Okay, so let's focus close to the screen. So check this out. On my phone, my actual location is 41 degrees north. And look, they've broken it down into arc minutes and arc seconds because you get super accurate position location with your GPS and your phone. So mine's 41 degrees, 49 arc minutes, and 23 arc seconds. And I'm located 71 degrees west, 24 arc minutes, and 51 arc seconds. Remember how we had to put coordinates into that form in our homework? So you can see that that's something that people do. How about anyone else? Does anyone else have a slightly different position who might be located not in Providence?
Ours is close.
I do.
Hit me. Where are you? Well, where are you, Cheyenne? Cheyenne, just read it to me because I can't see.
I'm in Newport. So it's 41 degrees, 31 arc minutes, 3 arc seconds north, and then 71 degrees, 18 arc minutes, and 40 arc seconds west.
So we're separated by more latitude than longitude. So you were like 31 arc minutes and I'm 49 or something. So we're like maybe 10 arc minutes away from each other on Earth. We could actually convert that into a distance. I'm tempted to do that as an exercise, but I've got too much other stuff to do. Anyways, it's kind of cool that you can get your location to such a high degree of accuracy and, you know, keep track of your position on Earth. I've got more to say about that, but let's leave it alone for now. Let's get into the other two coordinates before we run out of time. I know the rest of you were going to tell me too, but screw it. Okay. Wait, I've got to adjust the focus. Focus. Okay. So let's now move on to the horizon system. The horizon system are coordinates that describe a star in your local sky. They also use two angles. The angles are called altitude and azimuth. Altitude is defined as the degrees of a star above the horizon. And technically speaking, it's the degrees above the nearest horizon. Okay? Azimuth is defined as the degrees measured along the horizon, measured clockwise from north. Let me show you a picture to help us understand. Okay, here's a star, and notice that, okay, they've done a wacky thing where they've rotated north over here. Let me choose red because it'll pop out a little bit more. The star is located up here on the sky. To find the star's altitude, you find the nearest place on the horizon, And then you just take your thumb or a sextant and you ask how many degrees up from the horizon are they? In this case, I'd say that star is maybe 30 degrees or so above the horizon, maybe a little more, maybe 40 degrees above the horizon. The azimuth doesn't measure how far up you are on the sky. It measures where you are along the horizon. So you start at north, and north is defined as 0 degrees. And then you swivel clockwise only along the circle until you get to that point. That's your azimuth. Considering that there's 360 degrees in a circle, if this is 0 degrees, I'd say that's 90 degrees, that's 180 degrees, and maybe that's 270. So maybe that azimuth would be like 300 degrees azimuth, something like that. Okay. Notice that azimuth is the same thing as direction. So for example, the azimuth of north, the direction north, is 0 degrees. East would be 90 degrees. South is 180 degrees. And west is 270 degrees. If you want to try altitude, what's the altitude of the zenith, class? Try to answer a question. What's the altitude of the zenith? Nick, were you going to answer and then you thought better of it?
Yeah, 90 degrees.
Good, thank you. Okay. We've got one more coordinate system to do, and then we can take a little break. The horizon system is really useful if you're out at a telescope with a friend or with your grandma, because then you can sort of collectively point to a place in the sky and you can say, hey, check out this star. It's 30 degrees above the horizon. In fact, a lot of modern telescopes use an altitude azimuth mount. Let's look up one of my favorite telescopes, a plane wave 1 meter telescope. This is the kind of thing that just, you know, really gets my juices flowing here.
How does that even work?
Well, first you shell out $200,000 and then you deliver it to your friend Brendan Britton, and the technicians install it in your observatory. I want to, this is actually a video. What the shit is going on here? Hold on. I think I might be zoomed in. Function, oh wait, control. Yeah, okay. So this telescope, it's just a really fancy telescope, okay? The one I have in the observatory is not this nice. It has an altitude and an azimuth mount. So you have a computer that controls this, and you can see these fork arms here will kind of swivel the telescope up and down. That's swiveling it in altitude. And then it can rotate around in a circle. That's azimuth. And I think they actually have a video of this thing in action. YouTube plane wave 1 meter telescope. I thought they did. They used to have a just kind of a nice one of not the installation, but of someone just kind of slewing it around. I really don't have time for this. I shouldn't be fucking around here. Look at these bastards in Utah. They got their plane wave. Why didn't I get my plane wave for Christmas? That's what I want to know. Let's get rid of the exciting music here. I just want to see if they'll show the thing swiveling. Yeah, you have to put it in your observatory with a crane. Get rid of your lame music. All right. I was hoping they would show this thing in action. You got to have people install it for you. Oh, there they are. You can take amazing pictures. So here you can see they open up the shutters of the dome. It swivels up and down to point to the star and it rotates around. And why do you want a plane wave 1 meter telescope? So you can take beautiful pictures of nebulae and galaxies and you can share with your friends. Anyways, you can also do some hardcore science research with it. The problem with the horizon system is as stars rotate through the nighttime sky, they're constantly changing their altitude and their azimuth. So it's a little annoying because your telescope has to be attached to a computer to keep tracking the motions. Another issue is, let's say you discover a cool thing like a nebula and you want to call it the Brendan Nebula so that everyone will know how cool you are. You find the position of your Brendan Nebula and you call all of your astronomer friends in Utah and you say, hey, check out the Brendan Nebula. I just discovered this. And they say, well, where is it? And you say, well, it's 30 degrees above the horizon. And then you stop and you start thinking, wait a minute, if it's 30 degrees above the Rhode Island horizon, is it going to be 30 degrees above the Utah horizon? No, it's not, because we're at different latitudes on Earth. And then you start to realize what I really need is a set of coordinates that is stuck to the sky, right? I need kind of like latitude and longitude for the celestial sphere, so that when I discover the Brendan Nebula, I can tell you it's this many degrees north and south, and every astronomer will know that they can't claim that nebula because I claimed it for myself, okay? Doesn't actually work like that, but let's just pretend it does. Okay, this is the equatorial system. It's our third coordinate system, and it's what we are going to be using today for our lab. So let's get to that before class ends. So the third coordinate system, and this is the most confusing, is called the equatorial system. And you can think of this as like latitude and longitude for the global sky. These are global sky coordinates because they don't depend upon your position on Earth. Everyone recognizes the same angles. They're a little bit funky, okay? One of the angles is called declination. And the other angle is called right ascension. Astronomers have nicknames for these coordinates. They refer to the declination as dec, and they refer to the right ascension as RA. So you'll hear me doing that even without thinking about it. I just say RA and dec, you know, that's how they do it. Now, to give you a bit of orientation before I define them, declination are kind of like your lines of latitude on the sky. And the right ascension are kind of like your lines of longitude on the sky. So let's define declination. Declination is like latitude, but instead of using the Earth's equator, we're of course going to use the celestial equator. The only main difference is instead of doing degrees north or south, we instead call them degrees positive or degrees negative of the celestial equator. So declination measures the degrees of a star, positive or negative, from the celestial equator. So to give you an example, kind of like the North Pole on Earth, the declination of Polaris, which is pretty close to the North Celestial Pole. I'm about to tell you a lie here. I'm going to lie to you. The declination of Polaris is positive 90 degrees. In fact, if I were to look up Polaris, Polaris, the star, they have this equatorial coordinates here. You can see that the declination is actually technically positive 89 degrees and 15 arc minutes. So technically speaking, Polaris is 3/4 of 1 degree off from the North Celestial Pole. It's not exactly there, but we're going to forget about that and we're going to lie and tell you it is there. Okay, now let's talk about right ascension. Right ascension is like longitude, but here's where things get a little bit weird. The first issue is you cannot use the prime meridian to define longitude. And that's because Earth is rotating underneath the sky, and the prime meridian is sweeping through different positions on the celestial sphere. You've got to pick a point that is on the celestial sphere itself to be the 0th position of right ascension. That's one issue. We're going to pick a point on the celestial sphere. The second issue is that for reasons which are not going to be obvious to you right away, instead of measuring the coordinate in degrees, astronomers measure right ascensions in hours, minutes, and seconds. And that's going to sound real weird at first, but let me explain why that's okay. If you're on a rotating Earth, okay, so if you're on a spinning Earth, Earth spins through 360 degrees in a day. And that means the sky rotates through 360 degrees in a day. Earth spins once in a circle, the sky spins once in a circle. And as you know, that takes 24 hours. Class, what do you get if you divide 360 degrees by 24 hours? Punch it into your calculator. That's your job.
15.
Exactly. Watch my units. 15 degrees per hour. It's not a coincidence that that came out so clean and even. The Babylonians actually invented the hour so that the sky would be broken up into 15-degree wedges. All of the timekeeping is based on this. So for astronomers, there's a conversion factor that's unique to astronomy, which is 1 hour is equal to 15 degrees of sky rotation. So I can measure my right ascensions in degrees, but I can also measure them in hours if I want to. And the reason why I want to is when you're at a telescope, it helps you quickly figure out how long a star will be up in the sky and how long you have to wait until it comes up in the sky. So there is a good reason to make it in hours rather than degrees. But for now, I just want to show you that the two things are kind of equivalent. Okay, I got to erase this. Let's get to defining right ascension here. Right ascension, by the way, the position that we're going to measure right ascension from is a point on the celestial sphere known as the spring equinox. And you've learned about the spring equinox already today. You learned that the spring equinox was a position in Earth's orbit. But the spring equinox is also a point on your celestial sphere. It is the point where the ecliptic, definition number 2, intersects the celestial equator. And that is an actual point on your sky. If you're curious about where it is, sorry, there's a lot of buttons fighting each other here. You guys can't see what's going on. Okay, here. On the sky, where are we? The spring equinox is a point located somewhere in the constellation Pisces. It's just a blank point on the sky, but it's below the constellation Pisces. And that's the position we're going to use to measure right ascension from. So we define our right ascension as the hours and minutes of a star measured eastward from the spring equinox. Damn it. I'm over time, class. I didn't realize that I had done that. I'm sorry. Okay. I had to get to that point for us to do our labs today. I apologize for that. Well, we can practice it during the lab, I suppose. Okay. Let's take a break for safety's sake. All right. I'll give you guys about 15 minutes. I'll pause the recording, and then we will crank through our lab. Okay? Sound like a plan, everyone? So I went a little bit over time. Apologies. Oh no, according to my computer, it says 132. Once again, my phone says 136. So I was going off my computer when I started class. So I'm a little. I got to figure that out. Okay. So I will give you until I guess on your iPhones, if yours match mine, 145 on my computer would be 147. I don't know. 150 on our iPhone. Do your phones say 137 right now? Is that what your phones say? So let's go to 150. We'll rejoin. Does that sound like a plan? And Mateus, if you think of it, don't let me forget to hit record because I did that yesterday. Okay. I'm going to pause the recording, in other words, right now, but don't let me forget to unpause it. Okay. All right. See you in 15. Okay. Hello, everyone. It's time for us to do lab 2 on celestial spheres. This lab is easy and fun, so let's get it done. I need something for my mouse here. It would help if you could do things in pencil. If we make any mistakes, it always looks better than when you scratch out pen. If you have nothing but a pen, I suppose you'll have to use pen, but pencils are always better, especially for homeworks. Okay, I've got my celestial sphere. We're going to practice our coordinates.
Are we going to be doing stuff on like scrap paper and then copying it over to the lab, or are we just going to go right to like writing stuff on the lab paper?
Excuse me, I'm dying here. We're going to just go right on to the lab.
Okay.
That's usually the plan. Move this in there. Okay. Just getting my feng shui going here. All right, so one of my former students was kind enough to give me an iPhone 7. So that has a much better, Mateus, you'll remember how bad my camera was last semester. My iPhone 5 isn't cutting it anymore. And someone actually gave me an iPhone 7 because they were so sick of my labs being on that crappy camera. So this should be a little better. Let's see if I can activate this and get it going here. I'm going to, I kind of set this up just to use, press home to unlock. This haptic touch thing is not, it's weird. Okay, share screen, share iPhone, share. And now I will do that. Screen mirroring, Zoom be Britain. Cross your fingers, hope this works. Come on. Ah, there we go. Okay, so now camera mode. Okay, how we looking? You guys see my paper okay? All right. So let me use this roll of tape here. Of course, we should always start with our names. So please put your name down. And of course, this is lab number 2. For your own records, it's not a bad idea to do that so that we can keep track of this, especially at the end of the semester if there's some dispute about whether or not a lab was done or done properly. And then of course, let's put the class, Astronomy 1020. And then please put your section. I hope you guys have figured out what section you're in. Your possible sections are 001, 002, or 102. You're in one of those three sections. So just choose one of those depending on which one you are. We're going to practice equatorial coordinates. We've got this globe here. Hopefully the glare won't be too bad and we can sort of see how it works.
I'm sorry for interrupting, but I don't think I have the same paper.
Okay, well, let's figure out what's going on there.
I'll tell you, I printed out the one that says lab 2. Let me show. Oh, I'm not.
All right, who am I talking to? Sabrina, hold that up for me. You see? Yeah, so what you did is you printed out the docx version instead of the PDF. But Sabrina, it should be the same. Do you see table 1 positions of 10 bright stars?
It says table 1, RA is 643 and degrees is 17.
Look, Sabrina, just look at my screen for a second. If you were going to print it out, and this could be useful going forward, you probably should have printed out the PDF, which has better formatting.
Okay.
See? But instead, I provided the same thing converted into a Microsoft Word document. That was in case you wanted to, all right, I'm just going to save this. That was in case you did not have a printer. You could fill this in using Microsoft Word, but you just kind of clicked the first one and printed it. So you printed the Microsoft Word one. But look, it's the same table. It just looks a little different than mine. You've got positions of 10 brightest stars. It's the same thing. It just looks weird.
All right, just want to make sure.
Okay, all right. Yep, you're good. Let's talk about some issues before we get going here. Constellations are more than just stick figures in the sky. Mateus, how many constellations are there in the nighttime sky?
I don't know.
Does anyone know? I thought I told you this last week.
Was it 18? Is it? I forget. Is that 18?
Wait, what was the question again? I'm sorry.
How many constellations are there on the celestial sphere?
Oh my God. 13?
77, something like
No,
that.
that's the zodiac.
You're close. 77 was warmer.
Wait, 88?
88, Mia. Very good. There are 88 constellations recognized by the International Astronomical Union.
I'm surprised I remembered that.
That's good. I can't believe you did great with that. Okay. Now listen, the constellations are more than just the stick figures. The constellations represent areas on the sky that are drawn around the stick figures. So that way, every position on the celestial sphere is associated with one of the 88 constellations. For instance, if you're a galaxy and you're located here, you are technically in the constellation of Orion because you are within the boundaries, okay? Several times during this lecture, during this lab, we're gonna find an object and we're gonna try to figure out what constellation it's in. And we're not gonna wanna cross the lines between the constellations. So now that I've explained that, let's go back to the phone here. Okay. Nope. Oh my God, it appeared and then it disappeared. All right, this is a problem. Sometimes this happens. Okay, we just use the force. Hope that it works. I should never, once I get a good link, I should never stop it because, come on. Shit. Now I'm in trouble. All right. Here's what I'm gonna have to do. I'm gonna have to shut
Professor, I have a quick question.
Yeah.
Oh, sorry, you go.
Okay, on my iPhone 5, there's a button on the top to shut things off. I have to reboot this iPhone, but I don't know how to use the iPhone 7. Is it the side button? How do
Isn't
I?
it still like you hold the home button and then the power button at the same time?
Where is the power button?
It's, oh God, I don't know on the 7. I mean, on my 6, it's on the right side.
Okay.
Press down on all the buttons.
Yeah, if you like hold it for like a few seconds, it
Well, I
should
need to be able to
restart.
turn it back on again too. That's
Yeah, it will come back on.
I need to turn, you know what else I need to do? I need to turn off Siri because I haven't mastered, I know I seem like Grampy using the internet here, but I haven't mastered the difference between clicking to the home screen and it keeps calling up Siri. I don't use Siri on my phone, so I need to, where do you turn Siri off? Oh, this is so irritating. Siri and search. Listen for Hey Siri, press home for Siri. Turn off Siri. Yes, okay. Fuck you, Siri. I don't want to deal with you. All right, that's much better. Now, second issue is how do I, let me just try this one more time here. Screen mirroring, come on, baby, please work. No, once I lose it, you have to restart the phone. It's really fucking annoying. It's, wait, let me try to, once I get a good link with the phone, I should never ever stop it because turning it on and off really pisses this thing off. It's not a good design.
I can show you from my phone. I think my phone's only one generation older than yours or newer than
yeah.
yours.
Yeah,
I can try to show you.
Yeah, I'm sorry. How do you do it?
All right. So my home button is right on the right side of the phone, like when you're looking at it. So you're going to hold the home button, this one down here, and the power button at the same time. So it's going to keep going, and you just hold it for a while, and then an option's going to pop up.
It's giving me Siri.
Wait, does the iPhone 7, because I know the previous iPhones, you could actually like push the button, but then in the newer generations, you don't actually push the button. It's just like,
okay,
you know what I mean.
So if you actually just hold down the power, just try holding down the power button instead of the home button, and then this screen pops up.
Yep, that was it. Thank you.
Okay.
Jesus Christ. Okay, fucking A. I'm sorry, guys. I use a different phone. This is just so that you guys have a better view. Trust me, you don't want to use the camera on my phone. And plus, people are texting me all kinds of annoying and embarrassing things all day. So you don't want to see some of those texts. All right, here we go. So let's power this thing back on. Pray to something. All right, here we go. Usually if you reboot, it kind of fixes itself.
Now that we're kind of situated, can I ask my question?
Yeah, go for it.
All right. So I didn't get to print it out because my printer was being dumb and it just wasn't working. So I took screenshots on my iPad, and I can just draw like on my iPad. Oh, you can't see that. But would that be okay? Like if I just like, sent it in as I would? Okay.
As long as I can read it and it's legible and it's neat and the questions are readable, then that's cool. That's a great idea,
right.
Tiana. I can't believe I didn't think of that as an option. Okay, so fingers crossed, everyone. Here we go. Share screen, iPhone. Come on, baby. Humming. Yes, it's gonna work. Yes. Okay. Fuck yeah. All right, here we go. So we're back. Now look, the first operation that we have for us in table 1 is to locate the 10 brightest stars on the celestial sphere, the 10 brightest stars in the nighttime sky. And these are kind of 10 of the most famous stars that you can see at night. They haven't told us their names. They've given us their equatorial coordinates, right, ascension and declination. Our goal is to identify the name of the star and the constellation of the star. So let me bring the globe up here where the natural light is a little better. And let's see if we can make some sense out of all this, okay? So on this globe, using cue cards, the cue cards will be helpful here. For blocking some stuff. The globe is transparent, so you can read it inside or outside. So let's just look at Orion here. It's all printed backwards on the globe. You're supposed to kind of read it from the other side. Geez, it's actually kind of dark. Let me, the one thing that makes this lab difficult is the transparent globe is tough to look at with the camera. But if I turn the lights up, okay, so let's see if that helps us a little bit. On the globe, the stars are labeled in black. So you can see it says Betelgeuse there. The stars are kind of these yellow dots. They draw in the stick figures with hard blue lines. The names of the constellations are written in blue. I think, okay, turns out the desk isn't good. I think over here is a little better. I need to figure out the lighting. That's what's really tough about all this. All right, let's see if that helps a little bit. What does that look like for you guys? That looks a little better. So you can see the names of the constellations are in blue. That, for instance, is Triangulum. It's actually written backwards. You're supposed to kind of look through the globe, but that's not going to work very well with our cameras here. So there, for instance, is Aries. Now, do you guys see those little dotted blue lines? That's the boundaries of the constellations. Let's also orient ourselves so that we can see the coordinates as well. This is the seam of the globe. This is the celestial equator. What do you think the declination of the celestial equator is? Does anyone remember what declination is? It's like latitude, right? So what's the latitude of the equator? What's the declination of the celestial equator? Anybody?
Positive or negative?
But it's measured from the celestial equator. So if you're on the celestial equator, your declination is?
Is it 0?
Yes. So this is 0. That's positive 10, positive 20, positive 30, positive 40, positive 50. On the other side, this is negative 10, negative 20. Each line is negative, goes by negative 10. Now, the right ascension, remember, is measured in hours. So right here, this is the spring equinox. You can see it says 0 hours. And then you measure along. This would be 1 hour of right ascension. This here, it's all backwards. That line is 2 hours of right ascension. That hour is 3 hours of right ascension. Whatever. Let's just try to do this stuff, okay? You'll figure it out as we go. So in the first question, we're looking for a star whose right ascension is 6 hours and 43 minutes and whose declination is minus 17 degrees. So let's start here. This was 0 degrees right ascension. And we'll slide along until it's 6 hours and 43 minutes, which, you know, I had some tape here. I think last time I did this, I used this thing as a baffle. Let's see if that still works. Okay, so this is 6 hours of right ascension. That line is 6 hours. And they actually mark the minutes in 4-minute intervals shown here. So even though we're supposed to measure along the celestial equator, right up here they mark 4 minutes, 8 minutes, 16, 20. Well, sorry, the big tick marks are 20 minutes. I know that. So 4, 8, 12, 16, 20. That's how it goes. Okay, so if we're at 6 hours and 43 minutes, that's the 6th hour of right ascension. And this is the 7th hour of right ascension. So we should be about, if you think about it, 43 minutes is 3/4 of an hour. So we should go starting at 6 hours, 20 minutes, 40 minutes, and that's 44. So this line of right ascension right here, that's 6 hours and 40 minutes. It's halfway between 6 and 7. What's our declination, class? Read it to me. Come on.
17.
Minus 17. Be careful, okay? Be more careful. -17. So we go down 10, we go down 20, and then we go back a little bit. That's our star. What's the name of our star?
Sirius?
Sirius. And what's the name of the constellation?
Canis Major.
Canis Major, the big dog. This is the brightest star in the sky. It's located at the foot of Orion. They refer to Sirius as the dog star, and the constellation is Canis Major, the big dog. You can actually see Sirius in your sky tonight, except it's cloudy. Aren't we supposed to get snow?
I don't think so.
Where's the snow at? Anyways, you know what sucks about working from home? No more snow days. Ever think about that?
Yeah.
Yeah.
Okay, let's go to our next one. So you guys are going to read this out to me while I crawl around on the ground there. 737 and +5. So let's see if we can go from there. I'm going to take this off because it's not doing any good. Oh, actually, I know what okay, guys, it's coming back to me. You know what I did is I took the tape. I'm going to make a thing here. I used the tape and I attached it to the card, and then I could like stick it to the globe. Because the hard thing about doing this remote, guys, is I need one hand for the phone, and then I need one hand to do everything else. And sometimes it's not enough hands. So I can stick this. Oh, I did the line side. Shit. Okay, that was a fail. Let me try this one more time. I want this side to be the baffle. So wait, tape like this. And tape like this. Okay, that ought to help me a bit. Okay, so what's the right ascension again? Read it out to me.
737.
Okay. So there's 7 hours. This tangerine slice is the 7th hour of right ascension. This longitude is the 8th hour of right ascension. This is 20 minutes. That's 40 minutes. And if we subtract 4, that's 36 minutes. But we need to start here at the celestial equator because that's 0 degrees declination. What's our declination?
+5.
So if that's +10, this is roughly +5. What's our star?
I don't know how to proc. I don't know how to pronounce that.
Procyon.
Procyon. Okay.
Procyon. And what's the constellation? I know you have to read backwards here, but
Canis Minor.
Canis Minor, the little dog. Woo! I almost dropped this bad boy. Oops, sorry. This is why we use pencil. So today's lab is off to a slightly rocky start, but we're getting it. Canis Minor had some glitches today. Okay. Next star, 20 hours and 40 minutes, +45. So let me grab my card. And let's rotate over here. I need to get like a helmet cam or something. That's what I really need. Need a helmet cam. Okay. So somewhere between, okay. So it was 20 hours and 40 minutes. There's 20, there's 20, 40. What's the declination, students?
+45.
+45. So we're going to go up 10, 20, 30, 45. What's our star?
Deneb.
Deneb. And the constellation?
Cygnus. Oh, Cygnus. Oh.
Cygnus. Cygnus is a swan. And Deneb is the tail of the swan. They sometimes call it the Northern Cross. It's usually up in the summer and the autumn. 1948, +9. We'll try to speed things up here. So there's 1940, 44, 48, and +9 brings us right up here. That star is Altair, and the constellation Altair, and the constellation is Aquila. Aquila is an eagle or something. Altair and Aquila. Okay, some old-timey time astronomy here. 5 hours and 13 minutes, +46 degrees. So 5 hours and 13 minutes. Was it positive or negative declination?
Positive. Positive.
Okay, sorry. It's not as easy as it looks doing this. So 5 hours and 13 minutes, 4, 8, 16. So somewhere around there is 5:13. And then +46, Jesus, +10, 20, 30, 46. There's our star. Capella. And Capella is part of this guy, Auriga. Auriga the herdsman. Auriga is up in your nighttime sky tonight, by the way. I noticed it this weekend. I was showing a friend of mine some of the constellations. Kind of a cool, fun thing to do when you're out at night. Okay, 513, -8. So that's still 513. We're going to drop down to -8. Now, this is in the constellation Orion. That foot is Saiph, but this is our guy. This is Rigel. So that's Rigel in Orion. If you notice, guys, do you see how this one's kind of on the other side of the globe? Let's jump ahead and do number 8, because that's near where we are now in terms of right ascension. 553 and +7, okay? So here's 5 and here's 6, 40, 44, 48, 52. So we have to start at the celestial equator about there. And +7 brings us up there. Pardon?
Nothing, I was just reading. Oh, wait, let me mute. I'm sorry. I just talk to myself out loud sometimes.
I do the same thing. I understand. What's our star?
Betelgeuse.
And that's also in Orion. So let's skip a line. All right, now we got to go back and get number 7 here. 1410 positive. Ugh. I'm going to drop this fucking thing one of these days. All right. So let's see if we can go to 1410 now. Okay, so 14's way in. Ooh, I don't think I can get my hand through there, so we're going to have to do it without the baffle. I don't want this thing to crash. So this is 14. 1410 would be like there. What's my declination again?
+19.
So +10, and that's +20. So can you guys read that?
Arcturus?
Arcturus.
Arcturus, very good.
That makes sense.
Arcturus. No, this is tough to read going forwards, never mind backwards. Okay, and what's the name of the constellation?
Oops.
It looks like booties, but it's Boötes. Boötes. And that's Arcturus in Boötes. So Arcturus. I think one of the O's has an umlaut. So it's, hold on, let me stabilize my phone here. Oops. Ooh. What did I do? Okay. So it's Boötes. I think it's the second one that has an umlaut.
Yeah, it's the second one.
Oh, did you look it up? Thank you. Keep track. I like it when you guys like fact check me and keep track of that. How did you know that?
I'm typing the answers into my computer on the Word doc and it auto-corrected it.
It auto-corrected for Boötes?
Well,
That's
it
pretty
said
fast.
it was wrong, so I right-clicked to see what the spelling suggestion was, and that was one of them. So.
Oh, cool. I'm surprised that they had something as obscure as the constellation Boötes in their dictionary. That doesn't often happen in astronomy, you know? Cool. All right, keep track of me here. Okay, now we're going to 16, 27, and negative 26. So these are all kind of hard to get to with the cue card. So 16, what can I do for magnification? Okay. 1627 is about halfway to 30 minutes is half of an hour. So there's 1630. And then we're going minus 26, minus 10, minus 20, and there we are. There's minus 26. This is Antares, which means anti-Mars. And anti-Mars is in the constellation of Scorpius. Okay. And now 1836 and positive 39. So there's 18, 1840, 1836 is right about there. And I'm sorry, what was the positive 39?
Positive 39.
Positive 10, positive 20, positive 30, and almost to positive 40. What's our star?
Vega?
Vega.
And Vega is in Lyra, the heart. All right, let's take a good look at that. Make sure you've got all those answers. Okay. Now we're going to do a couple more tables, but they won't take quite as long. Let me just keep track of time here so I don't screw you guys over. We're doing okay for time. I wanted to finish in an hour, but it's going to go a little over that. So we're not going to go past 3. We just have 2 more little things to do, I think. All right, so let me get the globe up here. And we're actually looking for the positions of the planets tonight. So what I need to do is I need to look up an ephemeris table. And I can do that here on Google. I'm going to do Sun to Sedna. And an ephemeris table will give us, by the way, why don't you think they put the planets, why didn't they print the planets on the globe? Anyone want to take a guess why? Why wouldn't you put the planets on the globe?
Perspective?
Does the planets move?
Exactly. The Greek word for planet, planetos, means the wanderers. And that's correct. They move across the sky. So if you want to know where a planet is on a given night, you have to look up its coordinates in a table called an ephemeris. And that's what I've done. And I want you guys to write these values down with me. We're going to do the 5 naked eye planets. These are the only planets you can see with the naked eye. let's list their right ascension and their declination. I need a ruler here. Sorry, I'm kind of running out of space. I'm going to make a column for right ascension and a column for declination. Okay. Okay, right ascension and declination. You know what's weird is my other phone had a different, like, it had zoom out capability. I don't know why this one doesn't. Okay, so the right ascension of Mercury is 2148. And sorry, I didn't leave a lot of room there. The declination is -12 degrees. Venus is 1938. I should have made those columns a little bigger. And -22 degrees. Mars is 2 minutes and 2 hours and 28 minutes. And +15 degrees. Jupiter is 2045 and -18 degrees. Saturn is 2028. Oops, that's 2028. And -19 degrees. All right, let's see if we can find which constellation each of these naked-eye planets are in tonight. And these are the coordinates for tonight, by the way, so this should be approximately true. So Mercury is 2148. Let's see if we can do this here. There's 21. A little more glare over here. What happens if I turn this down? Does that reduce our glare? It's a little better, I think, right? Okay. 2148 is like 2150. So that's almost at 22. And then we're going to go -12 degrees. Notice we just crossed a dotted blue line. So we should go down here. And it says Capricornus. 1938, -22. So there's 1938 minus 10, 22. Nope, there's a dotted blue line there. I don't know if you can see that. So we're drifting over here. That's in Sagittarius. Mars, 228. There's 2 hours. And 28 is almost 30. +15, dump, dump. What's our constellation? Can you see it?
Say Aries.
Aries. Jupiter is 2045 and -18. So 2045 is 3/4 of the 45 minutes is 3/4 of an hour. So if that's 20 and that's 21, I'm going to go right about there. That's 2045. -18 is -10, almost -20. Looks like that's also in Capricornus. Saturn, 2028 and -19 degrees. So sorry, 2028 is once again almost 2030, and then minus 10, almost minus 20. That's also in Capricornus. Can you guys see how there are 3 planets in the same constellation?
Mm-hmm.
That's called a conjunction, when planets line up together. Recently, we had a very close conjunction of Jupiter and Saturn. They were so
Oh, I
close.
saw that.
Did you guys see that?
Yeah, I saw it a couple of days before like its biggest, you know, I don't know, most visible, but I noticed it and I was like, whoa, that's cool. And then I
What was
kind
so
of
cool is on that particular day, they were only separated by 1 arc minute. That's less than your human eye can resolve. So on that day, they got so close together that the 2 stars kind of blended together to make one big bright star. And it was a little cloudy that day, but I took the telescope up to the Peerless roof next door. And when I looked into the viewfinder, I tried getting a picture, but it was kind of lousy. You could see like Jupiter with its little stripes, and you could see Saturn in the eyepiece together. It was really beautiful. It was very, very cool. That was a kind of a once in a lifetime conjunction there. So conjunctions happen all the time, but to have them be that close was really special. Unfortunately, guys, these answers are not exactly correct. Now, I don't know if you can tell by the construction of this globe, but CCRI has had these things for a long time. And these were probably made in the 1980s. And in the 1980s, they were actually using something called 1950s epoch coordinates. So what happens is Earth goes through these gravitational wobbles because of the moon's influence, and it causes the Earth's equator to slip and shift relative to the ecliptic, and it eventually changes the positions of the stars. So if you look at my laptop here, let's see if I can go to the internet. I don't want to have that thing happen that happened before. Come on. There we go. You'll notice the actual constellations that they're in are a little bit different. For instance, they have everything in Aquarius, and they have Mars in Taurus. So that's off by about 1 constellation from where we are here, because since we're now in the year 2020, if you think about it, that's 50 years since this globe was made. And that means the positions of the stars in 50 years have actually shifted a bit. How am I doing on time here?
It's 2:37.
Okay. Now, we can also look up the coordinates of where the sun is. Now, the sun is the yellow nubbin, and the sun moves along the ecliptic. The ecliptic is this line here, and you guys will notice that the ecliptic has a bunch of dates printed along it. In the third table that we're going to do, we're going to move the sun to these dates along the ecliptic, and then we're going to try to figure out what is the RA in the deck. And I'm going to do this kind of quickly since we're getting short in time here. February, March 1st, March 5th, March 10, March 15, March 20, and that's March 21st. Let's move the sun right about there, okay? So there's the sun on March 21st. Now, you'll notice it's on the celestial equator. That means the declination is 0 degrees, because that's the celestial equator. But you'll also notice that it's on this line of right ascension, which is 0 hours. When we write right ascensions, we have to write them like a military clock. 00:00. So that's the location of the sun. On the spring equinox, the sun is on the spring equinox. I'll let you think about that for a minute. That's a sort of riddle that actually makes sense. Let's try moving it to June 21st, okay? So we'll slide along here to June. The 21st is about there. Can you guys see what your right ascension is?
Is that 6 hours?
Good.
Well, 6 hours.
And I want you guys to note the declination. So this is 0 degrees, right? The sun's position is a little goofy, so we got to go up 10, up 20, and the sun doesn't perfectly line up, but the 21st is actually right about there. And so it's about positive 23. In fact, it's technically positive 23.5 degrees. That's what it's supposed to be. That's the summer solstice. Let's go to the fall equinox now.
This would have been a lot better in person for sure.
I know, guys. Honestly, I've done this better in previous years. I'm not quite used to the new phone, so it is way better in person. Exactly.
That's why I'm trying to figure it out yourself and everything.
Yeah, it's honestly, I could have done more prep work on it, but usually my policy is just to wing it, you know.
You know what might help with the camera?
What?
If you get like one of those like the tripods that have like the bendy legs, that way you can kind of just like place it so you don't have to hold your phone. Yeah, that might work.
I actually shelled out for like a GoPro and all this stuff, and it was just so confusing to get all the wires together. I need like a day or two to do it. I haven't really figured out how to make it work yet. If any of you are like home gamers who like stream your shit on Twitch and you want to give me some tips, a tripod is actually a great idea though. I should get something like that. Right now, this is my tripod. It's okay. All right. So September 21st is that's September 20th, and that's September 21st. You'll notice once again, we're back on the celestial equator. So our declination is 0 degrees. And our right ascension here is 12 hours. And now we'll go to December 21st. All right. So there's there's December 21st. It's right about there. So we're at 18 hours of right ascension, and we're down positive 10, positive 20, and a little bit more. We're supposed to be at negative, sorry, not positive, negative 10, negative 20. We're supposed to be at negative 23.5. So it's 18 hours. All right. Now, today, what's the date today?
25th, 26th.
1/26. So let's slide over to January 26th. I would say that today we're somewhere between 20 and 21 hours. So it's about halfway through. Let's say 2030. So this is 1/26. Sorry. And it looks to me, what would you guys say the declination is there?
$21 degrees.
Well, hold on. This is 0, right?
Oh.
You're down from 0.
Like
25?
15?
Huh?
Is that 25?
Is it?
On the camera.
What's, hold on.
Is it 15?
Like negative 15.
Yeah, negative 15 cents.
Negative, yeah, because you go down. That's right.
You're down. That's what I wanted you guys to recognize. Okay. Now, we're pretty much done, but I want to do one last fun little game with you guys, okay? And then I'll stop. In the same way that I can move the sun to any one of these dates and get its coordinates, I can also move the sun to any one of these dates and I can figure out what constellation it's in. For instance, today, the sun is in the constellation of Capricornus. That means Capricornus is up right now in the sky. Oh, look, it's starting to snow. I don't know if you can see that. So one of the things is this is the basis for how astrology is supposed to make its predictions. Your birthday is connecting somehow to what constellation the sun is in, and then it's going to send vibrations from the sky and bop you off the head, and that determines your personality or something. Of course, the thing is that all of those constellations they put in the newspaper and in your co-star are based off Ptolemy's Tetrabiblos, which was published in like, I think 500 AD. So let's see, 2020 minus the year 500, that's 1,500 years out of date. And if the coordinates shift a little bit from 1980 to 2020, imagine how much the coordinates have shifted in 1,500 years. So let's take a student like, I don't know, Sabrina. I saw you first today. Sabrina, if you don't mind, what's your birthday? Just give me the month and the day.
6/25.
So you're 6/25.
You want us to write this or just watch?
Just watch. Sabrina can write it. The rest of you can wait. So this is Sabrina's birthday, 6/25. And what is your sign supposed to be according to like the newspaper or co-star? Pardon?
Cancer.
So in theory, she's a Cancer. And so April, May, so you're June 25th, right?
Mhm.
All right, gonna make sure I get this. Why don't we move the sun to June 25th and let's see what constellation the sun is in. So here's February, March, April, May, and we're gonna move the sun to June 25th. There it is. So there's the sun. The sun is in June 25th. You can see there's a boundary to the constellation there, and you are clearly past that boundary. So that's June 25th is past the dotted blue line, which is behind it. So what constellation was the sun in when you were born, Sabrina?
Gemini?
Yep.
What
So
the
guess
hell?
what? You're not
Right.
a Cancer anymore. You now have a new sign.
Doesn't it all
Actually,
time of, like time of birth?
say that.
Doesn't it also go off the time of birth?
Okay, well, but the day is like a little fucking wiggle on this globe, right? So look, that's the difference between June 25th and June 24th is that, so the day is only like this. The sun doesn't drift enough in one day for it to affect the constellation. Do you understand, Mia? It's not gonna, 24 hours isn't gonna send the sun careening across the sky. It takes a full year for the sun to drift. Mia, a good rule of thumb is the sun drifts 1 degree per day along the ecliptic. So if you wiggle by 1 degree back and forth, that's not going to change it. The point is this: Sabrina up to now has believed that she is a Cancer and she reads the horoscope for Cancer. But if you're supposed to be, if your sign is supposed to be based on where the sun was on your birthday, what does it mean that the sun was actually in Gemini when Sabrina was born? Sabrina, I didn't ask you for the year, but I'm pretty sure the year wasn't 500 AD, right? You weren't born in 500 AD. So the day you were born is a lot closer to these coordinates than they are to those coordinates. You see what I mean? And
Yeah.
I don't have time to do this with, but so what is Sabrina? Is Sabrina a Cancer or is she a Gemini? I don't know. Depends what kind of peace pipe you're smoking, you know, like it's.
Oh my God.
So
Everything I know
anyways,
is a lie.
let's just try it, you know, for one more person just for fun. Cheyenne, how about your birthday? What's your birthday?
Mine is actually not too far off. Sabrina's. Mine is July 10th.
Okay, let's do one on the other side of the globe. Who's born like in the winter time?
Mine's in November.
February.
December 14th.
Hold on, let's.
Sabrina, we have the same birthday.
Oh, that's cool.
Yeah, I'm July 10th too.
That's cool.
That's awesome. We'll have,
Wait, there's Cheyenne. Oh.
We have a bunch of Cancers in here.
Kiana said November, right? I'm sorry, not
Yes.
Kiana. What November? What?
24th.
Okay, and what's your sign supposedly?
A Sagittarius.
Okay.
All these
Sometimes the sun hasn't, if the constellation is really big and wide, sometimes the sun hasn't drifted enough and you'll still be in the same sign. But let's see let's see. I tried demonstrating this to one of my friends, and the sun was still in the same constellation as their sign. They were like, "See, I told you so." And I was like, "Motherfucker!" So, all right, anyways, we'll try one more here. Let's try. So November 24th is supposedly Sagittarius. So here's November, and oh wow, you're right on a cusp here. So let's be very careful. November 24th is like right there. So it's actually it's almost on the dotted line, but it's actually a little bit over the dotted line, and it looks like the sun was actually more properly in Libra.
That's so weird.
Right? Exactly. So you're a Libra now, okay? It's all
What
different.
about February
I'm so invested.
All right, Nick, what's February? February what?
18th?
So here's February 20th. What are you supposed to be?
Aquarius.
Oh, wow, look at this. February 18th is actually still in Aquarius. So you'd be an example of someone whose constellation did not change. The sun hasn't drifted, or it has drifted, but it just didn't drift through the entire constellation. I think the general rule is you're usually about 1 month, you're about 1 month off from what the co-star says you are.
Can I make a quick comment?
Please.
So I don't know why, but like sometimes, because I like zodiac things like merch and all that stuff. And sometimes when I would look for Sagittarius stuff, like for my birthday, I would fall under Scorpio for some reason.
Okay.
Why is that? Like, why does it bounce back and forth between Sagittarius and Scorpio?
Because pretty much anyone who says I'm an astrologer can be an astrologer. Like if you just like put like a hippie bandana on and you like say that you're in touch with the stars, you are now qualified to be an astrologer. So what happens is there's all these different people who are doing it, and they're using all these different star charts. The majority of the ones you see in the newspaper are based off of Ptolemy's Tetrabiblos from 500 AD. But sometimes people who think they're going to break through the fourth wall because they took DMT or something, like those people will use some other star chart. There is even a sect of astrology that uses more modern star charts and will use the actual modern position of the sun. So the thing is, whoever's knitting those socks, or I've got some cool socks with constellations on them too. So I understand why you'd be into the merch, because it's kind of cool to have like some star themed merch.
Yeah, I got a constellation calendar.
Me too. I have a beautiful lunar calendar that I hope to show you guys at some point. So I'm into that kind of shit. It doesn't mean that I can't get into like the aesthetics and stuff. But the problem is whoever knit your socks, who knows what star chart they used? It could have been from 1950. It could have been from 1857. And the sun's been drifting around due to precession during that time. So there's no way to check the person's credentials or their bona fides. You know what I mean?
Mm-hmm.
Anyways, I thought I would try to demonstrate that it's not as simple as the astrologers will have you believe. Okay, it's fun. It's just for fun. Okay. All right. So just don't go draining your bank account or pay money to any cult or anything like that. You know, some people really do take it too far.
I'm gonna go start looking at Gemini and see if it compares to me.
Okay, there you go. Right?
I know, right? I gotta go look at my astrology book and be like, been living a lie.
Take the wrong message away from this lab.
Like I knew something was off.
Well, you've done it again, guys. You've wasted another 3 hours learning astronomy with me, and that was a good time. You guys all know what to do. You're going to submit this right away so that we don't get any zeros, right? Just these 2 pages. On Thursday, we will do a more lecture on coordinates and things like that, and then we'll have a homework session, okay? Thursday's homework session is going to be a little intense, I warn you, but we'll get through it. We'll try to get through it fast. Have a great Tuesday. Enjoy the snow, and I'll see you guys on Thursday, okay?
Thank you.
Thank you, you too.
Thank you.
Bye, everyone.